Section 4.1, Maxima and Minima. Alright, so I'm first going to start off with this rough sketch of a general function, just to make sure that we're all on the same page with the terms: maxima, minima, absolute minimum, relative maximum, relative minimum. So if this is our whole function, the absolute max is going to be approximately right here. That's what we would call our absolute max, or maximum. Okay, the absolute minimum would probably be this point right here. And then you can also see there's a couple other peaks and valleys, or at least one other peak and one other valley. So this is a peak. It's not the absolute maximum, but it's higher than the things around it. So we call that a relative maximum. And similarly, we've got a little valley here. It's not the absolute smallest value on this graph, but it's smaller than the things around it, so we call that a relative minimum. Alright, so a key thing to note, whenever we have a max or min, well, not whenever, but in this example, the derivatives exist because we've got a smooth curve. Hopefully you can see that when we have a smooth curve, when the derivatives exist at each of these points, the slope is 0. Alright, so we've got some theorems that relate all these things. We have theorem 4.1, the extreme value theorem, says that a function that is continuous on a closed interval AB has an absolute maximum value and an absolute minimum value on that interval. Alright, so this is a nice theorem. It guarantees the existence of an absolute max and an absolute min. But it's a very specific, there are very specific hypotheses. We need a continuous function on a closed interval in order to be guaranteed to have an absolute max or min. Then we also have the local extreme point theorem. If f has a local minimum or maximum at some point C, and f prime of C exists, then we say that f prime of C equals 0. So there's a couple ways to break this. For example, if I have the absolute value, the absolute value function, it looks like a v, right? Okay. Well, you can see that there's an absolute minimum which is also called the local minimum or a relative minimum, at 0, right? But f prime at 0 is not 0. F prime at 0 does not exist. Okay, so that's why we have to have, f being a local min or max at C and the existence of a derivative. If we have both of those things, then we know f prime of C is 0. And then the last, one of the key points of this section is the critical point. It's an interior point C of the domain of f, so some function f, at which f prime of C equals 0, or f prime of C fails to exist. And we call that point a critical point. So, all of the relative or local mins and maxes that I drew initially, okay, those are all going to be critical points. F prime of C equals 0 at all of those points. And then this absolute value example that I just gave you, f prime of 0 does not exist. Okay, so that would also be considered a critical point. Alright, let's see an example. So suppose we have the function f of x equal to 3x cubed plus 3x squared over 2 minus 2x, and we're given a specific interval, minus 1 to 1. So we want to find the critical points of this function, then we want to find the absolute min and max. So, is this function continuous? Yes, it's a polynomial. Polynomials are continuous everywhere. Okay. So this polynomial, this f of x, is continuous on the closed interval -1 to 1. So we are guaranteed by the extreme value theorem that an absolute min and an absolute max exist. So let's start by finding the critical points. So f prime of x is equal to 9x squared plus 3x minus 2. Now to find the critical points, we set f prime of x equal to 0. Okay, so solving this equation tells us the critical points. Alright, so we have 9x squared plus 3x minus 2 equals 0. I can go ahead and factor this into 3x minus 1 times 3x plus 2 equal to 0. So that gives us x equal to 1/3 and minus 2/3. Okay, so those are our critical points. Alright, so how is this going to help us find the absolute minimum and the absolute maximum? Well, if you've got a continuous function on the closed interval, the absolute min and max are going to occur either at a critical point or at the endpoints. So now to figure out what the absolute min and max are, we test the endpoints and we test the critical points. We test the function value at all of those points. So, f of -1, the left endpoint. If we test the function value at that point, okay, I'm just plugging in -1 for x. Okay. If we evaluate that, we get 1/2. If we also test the right endpoint, okay, well, the right endpoint gives us 3 times 1 cubed plus 3 times 1 squared over 2 minus 2 times 1. That gives us 5/2. Now I test the function value at each critical point. So at 1/3, okay, I'm not going to, you follow the same procedure. If you follow the same procedure, it comes out to be -7/18. And if we test f of -2/3, we get a function value of 10/9. Okay, so that means that the absolute maximum is the biggest number that we have here. Well, the biggest number that we've got is 5/2. Okay, and that occurred at the right endpoint. The absolute minimum, so the smallest number we've got is -7/18. And that occurred at one of the critical points, which was the critical point 1/3. Alright, so, good luck exploring this concept. Do the practice problems. There's a lot of good homework problems here. And as always, let me know if you have questions.